In the annals of modern aviation, few machines occupy a space as distinct, confusing, and visually arresting as the Sukhoi Su-47 Berkut, which translates to Golden Eagle. To the uninitiated observer, the aircraft appears as a refugee from science fiction, a stark, menacing silhouette defined by wings swept defiantly forward, seemingly flying in reverse against the current of conventional aerodynamic wisdom. To the aerospace engineer and the defense analyst, however, the Berkut represents something far more profound than a mere visual curiosity. It stands as a magnificent, tragic experiment, a machine that solved one of aviation's most bedeviling problems, the aeroelastic divergence of forward-swept wings, only to be undone by the brutal economic realities of post-Soviet Russia and the relentless physics of structural fatigue. The aircraft, which bore the designations S-32 and S-37 during its gestation before being marketed as the Su-47, is frequently misunderstood. Popular media and video games often portray it as a fully operational superfighter, a peer competitor to the F-22 Raptor that simply never entered mass production. This characterization, while partially rooted in the aggressive marketing campaigns mounted by the Sukhoi Design Bureau during the late 1990s and early 2000s, fails to capture the aircraft's true significance and its actual mechanical reality. The Berkut was not merely a prototype for a frontline fighter. It was a desperate survival mechanism for a design bureau facing existential threats, a flying laboratory for advanced materials science that would eventually birth the Su-57, and a technological demonstrator that proved, perhaps too effectively, why the world's air forces have largely abandoned the forward-swept wing concept despite its theoretical brilliance. To understand the Su-47, one must look past the air shows of Moscow and towards the strategic requirements of the Soviet Navy in the early 1980s. The Soviet Union was in the midst of a massive naval expansion, moving beyond the helicopter carriers of the Moskva class and the vertical takeoff limited Kiev class towards true power projection capabilities. The ultimate goal was the Ulyanovsk-class nuclear-powered supercarrier, a vessel designed to rival the American Nimitz class in tonnage and capability. Such a vessel required a fighter aircraft capable of operating with heavy payloads, yet able to launch from a ski jump or catapult and recover on a short deck. The existing Su-27 flanker design, while formidable as a land-based air superiority fighter, faced inherent physical limitations in the carrier environment. Its long tail boom and specific lift characteristics at low speeds presented challenges for high-weight carrier takeoffs and precise landings. The Sukhoi Design Bureau, under the visionary leadership of Mikhail Simonov, began work in 1983 on a project initially coded S-22. The requirement was specific and demanding: a highly maneuverable fighter that could dominate close-range engagements, the knife fight of aerial combat, where Soviet doctrine believed future engagements would inevitably devolve despite the proliferation of beyond-visual range missiles. The unique constraints of carrier operations, specifically the absolute necessity for high lift coefficients at low approach speeds to ensure safe recovery, drove the designers toward an unconventional solution: the forward-swept wing. The forward-swept wing configuration offered higher lift-to-drag ratios at subsonic speeds and superior stall resistance, traits that were perfect for the perilous flight regime of carrier aviation. The S-22 concept was radical, initially envisioning a single-engine fighter that would utilize this wing platform to maximize low-speed control authority. As the project evolved, the ambition of the designers grew, and the single-engine S-22 concept morphed into the heavier twin-engine Su-27KM, which stood for Korabelny Modifitsirovanny, or Shipborne Modified. The designers realized that the forward-swept wing configuration offered advantages that extended far beyond the carrier deck. It promised a fighter that was virtually spin-proof, possessed varying degrees of inherent instability that could be exploited for rapid nose pointing, and offered a lower stall speed than any delta wing contemporary. The Su-27 was intended to be the hammer of the Soviet carrier battle group. However, the political and economic foundation upon which this project rested was crumbling. By the late 1980s, the Soviet economy was under immense strain, and the ambitious naval expansion plans were being curtailed. The Ulyanovsk carrier was scrapped on the slipway, and the formal requirement for the Su-27 vanished with it. In a standard procurement environment, the project would have been archived, its blueprints consigned to the vaults of the Ministry of Defense. The dissolution of the Soviet Union in 1991 was a cataclysmic event for the Russian aerospace industry. State funding evaporated overnight. Design bureaus that had employed thousands were left without contracts, direction, or money. Sukhoi, however, made a strategic decision that would define its future. Fighting for relevance and survival in a chaotic market, the Bureau decided to continue the development of the forward-swept-wing airframe using its own funds. The project was redesignated S-37. This change was not merely administrative. It signaled a pivot from a specific naval fighter to a broader technology demonstrator and a potential land-based air superiority fighter to compete with the Mikoyan Project 1.44 program. To make this feasible with limited funds, Sukhoi adopted a Frankenstein approach to construction. The S-37 grafted the forward fuselage, vertical stabilizers, and landing gear of the existing Su-27 family onto the radical new composite wing and center fuselage. This hybridization was a stroke of pragmatic genius. It allowed Sukhoi to put a prototype in the air for a fraction of the cost of a clean sheet design. However, it also embedded certain compromises into the airframe, specifically regarding radar cross-section and weight distribution, that would later fuel misconceptions about its stealth and performance capabilities. The aircraft, eventually marketed as the Berkut or Golden Eagle, and given the designation Su-47 in 2002, was a singular machine. Only one flying prototype was ever built, a solitary testament to the financial austerity of the era. The defining feature of the Su-47 is, without question, its high aspect ratio forward-swept wing. To the layperson, it looks backward, a mistake in assembly. To the aerodynamicist, it represents a tantalizing optimization of lift distribution that has seduced designers since the German Junkers Tu-87 of World War II. In a conventional aft-swept wing, the airflow over the wing tends to slide outwards towards the wingtips, what we call spanwise flow. This spanwise flow thickens the boundary layer at the tips, making them susceptible to separation and stall at high angles of attack. When the tips stall, the ailerons, which are located at the tips, lose authority. This results in a loss of roll control and a tendency for the aircraft to pitch up uncontrollably or enter a spin. The Su-47's wings sweep forward. This geometry reverses the spanwise flow, directing air inward toward the wing root and the fuselage. The result is that the wingtips and the ailerons located there remain in clean, energized air long after the wing root has stalled. This grants the Su-47 exceptional controllability at extreme angles of attack, arguably superior to the thrust vectoring solutions available at the time. The aircraft can retain roll control at angles of attack exceeding 45 degrees, allowing the pilot to point the nose at a target while the aircraft is essentially falling out of the sky in a controlled stall. Furthermore, the forward-swept wing design offers significant advantages in the transonic regime. It reduces wave drag and improves the lift-to-drag ratio. Structurally, the geometry allows the wing root to be located further aft on the fuselage while keeping the aerodynamic center forward. This moves the bulky main wing carry-through structure behind the cockpit and weapon bays, freeing up internal volume in the center fuselage, a critical factor for the Su-47's internal carriage capabilities. If the forward-swept wing is so aerodynamically superior, why is it not the standard for all fighter aircraft? The answer lies in a destructive physical phenomenon known as aeroelastic divergence. When a forward-swept wing produces lift, the aerodynamic force pulls the wingtip upward. Because the tip is forward of the wing root, this upward force creates a twisting moment that rotates the leading edge of the wing even further upward, increasing the local angle of attack. This increase in angle of attack generates more lift, which twists the wing further, generating even more lift. This creates a runaway positive feedback loop. In a conventional metal wing constructed of aluminum or titanium, this torsional force would rapidly exceed the structural strength of the material, ripping the wings off the airframe at high speeds. This barrier stymied the German Junkers Tu-87 and complicated the American X-29 demonstrator. To stop the wing from twisting itself into destruction, it must be made incredibly stiff. In metal, this stiffness requires so much mass that the wing becomes too heavy to be practical, negating any aerodynamic advantage. The Su-47 is not just a forward-swept wing aircraft. It is an unstable integral triplane. It features 3 distinct lifting surfaces: canards, which are all moving foreplanes mounted on the leading-edge root extensions, the main wings with their forward-swept lifting body, and horizontal tailplanes, traditional elevators, at the rear. This tandem triple layout is shared with the Su-37 Terminator and allows for sophisticated management of the center of lift relative to the center of gravity. The canards are primarily used to trim the aircraft during high angle of attack maneuvers and to generate vortex lift that energizes the airflow over the main wings. By manipulating these 3 surfaces, the flight control computer can decouple the aircraft's fuselage orientation from its flight path, allowing for unconventional maneuvering capabilities. The vertical stabilizers are canted outward, a design choice borrowed from the Su-27 but exaggerated. This canting helps to reduce the lateral radar cross-section by reflecting radar energy away from the source. However, the large size of the tails, necessitated by the inherent instability of the forward-swept wing configuration, compromises the aircraft's stealth profile from the side aspect. A curious and often noted feature of the Su-47 is the presence of 2 tail booms of unequal length extending past the engine nozzles. The port or left boom houses a brake parachute, a standard feature for Russian fighters operating from rough or short runways. The starboard or right boom, however, is longer and houses a rear-facing radar and potential electronic warfare equipment. This asymmetry is a hallmark of the Frankenstein nature of the prototype, utilizing existing flanker structural elements adapted for new roles, but it also hints at the advanced sensor fusion concepts Sukhoi was exploring. The existence of the Su-47 is entirely owed to advances in composite materials. Without the revolution in carbon fiber technology, the aircraft would have remained a paper study or a static sculpture. To solve the problem of aeroelastic divergence without making the wing prohibitively heavy, Sukhoi designers utilized a technique called aeroelastic tailoring. The wing panels of the Su-47 are constructed of nearly 90% composite materials by weight. The genius of this approach lies in the orientation of the carbon fibers. In a standard metal wing, the material properties are isotropic. They are the same in all directions. In a composite wing, the engineer can control the strength and stiffness in specific directions by layering the fibers. Sukhoi engineers laid the fibers in specific non-isotropic patterns to create a structure that exhibits bend-twist coupling. When the forward-swept wing bends upward under aerodynamic load, the internal structure of the composite material forces the wing to twist its leading edge downward, what we call washout. This counteracts the natural tendency of the forward-swept wing to twist upward or wash in. Essentially, the material itself fights the aerodynamics. The wing is programmed to deform in a way that sheds load rather than accumulating it. Before we continue, I'd love to hear from you. Have you heard about this incredible aircraft before? Drop a comment below and let me know what you think. If you're enjoying this deep dive into aviation history, please hit that like button and subscribe to the channel so you don't miss any of our upcoming videos. Your support really helps us bring you more fascinating stories like this one. This solution required manufacturing precision that was unprecedented in the Russian aerospace industry of the 1990s. The wing panels were produced by the Obninsk research and production enterprise known as Technologia, utilizing novel materials developed by the All-Russian Institute of Aviation Materials. These materials had to outperform anything available in the 1980s to survive the immense stresses of the forward-swept wing configuration. The production of these wings was a Herculean task. The panels were large, complex, and required autoclave curing at precise temperatures and pressures. The sheer size of the composite skins meant that any defect in the layup, a void, a wrinkle, or a misalignment of fibers could result in catastrophic failure at high G loads. The cost of these materials and the labor-intensive process of tailoring the fiber directions made the wings significantly more expensive than traditional aluminum or titanium structures. While the prototype proved the concept worked, it also highlighted a significant barrier to mass production. The rigorous quality control and exotic materials required for forward-swept wing aeroelastic tailoring were difficult to scale in a cost-effective manner. This difficulty was a contributing factor in the eventual decision to abandon the forward-swept wing layout for the subsequent PKFA or Su-57 program, which utilizes a more conventional planform that is easier to manufacture in quantity. Beyond the wings, the Su-47 utilized a mix of advanced materials throughout the airframe. The fuselage was oval in cross-section and constructed mainly of aluminum and titanium alloys, with 13% by weight composed of composite materials. This extensive use of titanium was necessary to provide the rigidity required for the central fuselage box, which bore the loads of the wings, the engines, and the tail surfaces. The integration of large composite wing structures with a metallic fuselage presented its own set of engineering challenges regarding thermal expansion and joint fatigue, further driving the research value of the airframe. For all its futuristic aerodynamics and space-age materials, the Su-47 was powered by engines that were decidedly firmly rooted in the past. This disparity between airframe and power plant was one of the defining contradictions of the Berkut. The prototype was fitted with two Avionics D30F6 afterburning turbofan engines. These were the same power plants used on the MiG-31 Foxhound interceptor. The choice of the D30F6 was a compromise born of necessity. The D30F6 was designed for the high-altitude, high-speed interception profile of the MiG-31. It is a massive, heavy engine optimized for straight-line speed rather than the dynamic throttle adjustments required in a dogfight. However, Sukhoi needed an engine with high thrust to push the large demonstrator through its flight envelope, and the D30F6 was available and powerful. The more advanced AL-41F engines were not yet ready, and the standard AL-31F engines of the Su-27 were deemed insufficient for the larger Su-47. Observers at air shows often noted the Su-47 leaving distinct smoky trails, a characteristic shared with the MiG-29 and other Soviet aircraft of the era. This was due to the combustion chamber design of the D30F6 and the fuel-rich mixture used at certain throttle settings. While acceptable for an interceptor like the MiG-31 operating in the stratosphere where visual spotting is less relevant, such a visible signature was a liability for a tactical fighter claiming any degree of stealth or low observability. The smoke served as a constant visual reminder that the aircraft was a demonstrator, not a combat-ready stealth fighter. There is considerable debate and confusion regarding thrust vectoring on the Su-47. While the aircraft's control laws and flight maneuvering logic were designed to integrate thrust vector control, the D30F6 engines installed on the prototype were not equipped with thrust vectoring nozzles in their standard configuration. Sukhoi planned to install AL-41F engines with thrust vectoring in later stages, which would have theoretically allowed the Su-47 to perform maneuvers like the Pugachev Cobra with even greater control. However, the prototype flew its career with the conventional D-30F6s. This is significant because it proved that the forward-swept wing design alone provided sufficient agility to rival thrust vectoring-equipped aircraft. The Su-47 could perform high-alpha maneuvers using only its aerodynamic surfaces, validating the inherent agility of the configuration. The Su-47 was an inherently unstable aircraft. Without a sophisticated digital flight control system, it would be unflyable, tumbling out of the sky the moment it left the ground. The aircraft utilized a quadruplex digital fly-by-wire system. This system acted as the intermediary between the pilot and the control surfaces. When the pilot moved the stick, they were not moving ailerons. They were requesting a roll rate or a pitch angle. The fly-by-wire computer would then calculate the optimal combination of canard deflection, flaperon movement, and tailplane angle to achieve that rate without overstressing the airframe or departing controlled flight. This system was a critical testbed for the algorithms later used in the Su-35 and Su-57. The software had to manage the complex interactions between the vortices shed by the canards and the forward-swept wing, a computational challenge that required significant processing power. The ability to seamlessly integrate the inputs from 16 control surfaces was a major leap forward for Russian avionics. The cockpit of the Su-47 was a blend of the old and the new, reflecting the transitional era in which it was built. While it was a test bed for modern glass cockpit concepts, early photos show a layout that retained analog gauges alongside multifunction displays. The pilot sat in a Zvezda K-36DM ejection seat. The seat back was inclined at 30 degrees to help the pilot sustain high G-loads during dogfights. This reclining position reduces the vertical distance between the heart and the brain, improving G-tolerance. A side-mounted control stick and a tensometric or pressure-sensitive throttle were used, prioritizing ergonomics for high-stress maneuvering. The side stick controller was a departure from the center stick found in most Soviet fighters, mimicking the F-16's approach to high-G control. Over the course of its life, the cockpit avionics were upgraded. It served as a testing ground for the avionics suite of the PAKFA or Su-57. While early iterations had a mix of dials and screens, later configurations incorporated large liquid crystal display, multifunction displays to display radar and tactical data, moving away from the steam gauges of the Su-27 era. These upgrades allowed engineers to test the human-machine interface concepts that would define the fifth-generation cockpit. One of the most significant but often overlooked contributions of the Su-47 was its role in developing internal weapon carriage for Russian fighters. Stealth requires clean lines. Hanging missiles on external pylons creates radar reflections and drag. Unlike the Su-27, which carries its missiles on external pylons and has a sculpted underbelly, the Su-47 featured a fuselage with a flattened bottom. This was not just for aerodynamics, it was to accommodate an internal weapons bay. This bay was critical for reducing the radar cross-section of the aircraft. By hiding the missiles inside the fuselage, the aircraft could maintain its stealth profile until the moment of firing. The Su-47 was used to test the UVKU-50 ejection launcher. In a high-speed dogfight or supersonic cruise, opening a weapon bay door creates massive turbulence. A missile cannot simply drop out. The airflow would smash it back against the airframe. It must be punched out through the boundary layer. The UVKU-50 is a sophisticated ejection mechanism designed to forcibly eject missiles, like the R-77 or R-74. While some Western launchers use pneumatic pressure, the specifics of the Russian system tested on the Su-47 involved robust mechanical ejection to ensure safe separation under high G loads. The Su-47 performed flight tests to validate that the bay doors could open and missiles could be ejected safely, providing crucial data for the Su-57's eventual weapon system. While the Su-47 never entered combat, its design specifications called for a formidable arsenal. However, it is important to note, that the single flying prototype flew mostly unarmed. The weapon bay tests were often conducted with dummy munitions to verify separation physics rather than live firing trials. The aircraft was theoretically capable of carrying 4 R-77 medium-range air-to-air missiles internally, with 4 to 6 external hardpoints for auxiliary fuel or additional munitions in a non-stealthy configuration, plus a standard 30mm cannon. The ghost of the Ulyanovsk carrier haunted the Su-47 throughout its life. Despite being rebranded as a land-based fighter, the physical evidence of its naval origins remained embedded in the airframe, offering irrefutable proof of its lineage as the Su-27 The Su-47 prototype retained the structural provision for a tailhook, a device essential for arresting wire engagements on a carrier deck but useless on a standard runway. Furthermore, the landing gear was heavily reinforced compared to a standard land-based fighter. Carrier landings are essentially controlled crashes, requiring gear struts capable of absorbing immense vertical impact loads. The Su-47's gear was built to take this punishment, adding weight that a purely land-based design would have shed. Perhaps the most smoking gun evidence of its naval heritage was the wing fold mechanism. In 2019, during its static display at the MAX airshow, observers noted the panel lines and hinge mechanisms indicative of folding wings, a requirement for hangar storage on an aircraft carrier where space is at a premium. For a land-based technology demonstrator, such a complex and heavy mechanism would be unnecessary dead weight. Its presence confirmed that the S-37, or Su-47, was built on the bones of the Su-27 naval fighter project, effectively repurposing the naval prototype for land-based testing. On September 25, 1997, Sukhoi test pilot Igor Votintsev took the S-37 into the air for the first time. The flight was a success, validating the basic handling qualities of the forward-swept wing design. Over the next few years, the aircraft flew an intensive test program exploring the edge of the flight envelope that had terrified aerodynamicists for decades. The testing was not just about proving it could fly, it was about gathering data on the complex interactions of the triplane surfaces and the structural loads on the composite wings. The aircraft became a staple of the MAX airshows in Moscow. Its alien appearance made it a propaganda coup for the Russian aviation industry, proving that despite the economic collapse, they could still produce world-class innovation. The sight of the black jet performing high alpha passes and tight loops wowed crowds and potential foreign investors alike. It was a symbol of resilience, a tangible proof that Sukhoi was still a force to be reckoned with. By the mid-2000s, the Su-47's flight program began to wind down. The decision had been made. The Russian Air Force would not pursue a forward-swept wing fighter. The PAKFA, or T-50, which became the Su-57 program, was selected, utilizing a more conventional planform. The Su-47 sat dormant for years, fueling rumors that it was rotting in a boneyard. However, in 2019, it was refurbished and placed on static display at MAX, a museum piece honoring its role in saving the industry. If the Su-47 was so powerful, why isn't it in service? The too powerful for its time hook is a romantic simplification of a complex engineering reality. The failure of the Su-47 to enter production was driven by a convergence of structural, tactical, and economic factors. The primary reason for the Su-47's non-adoption was the wing itself. Despite the composite tailoring, the wings were subjected to immense twisting forces. The stress of countering aeroelastic divergence meant the wing structure would likely have a much shorter service life than a conventional wing. The materials were working against the physics of the air every second of flight. Repairing complex, tailored composite structures in the field is difficult and expensive. A damaged panel cannot simply be patched. It might require complete replacement to maintain the aeroelastic properties. To prevent structural failure, the aircraft was often limited to speeds around Mach 1.6. While agile, it lacked the raw top-end speed of the MiG-31 or Su-27, limiting its utility as an interceptor. Forward-swept wings are inherently difficult to make stealthy. The complex geometry of the wing root junction and the way radar waves reflect off the forward-swept leading edge make it harder to align the planform for radar deflection. As fifth-generation requirements shifted heavily toward very low observability, the forward-swept wing design became a liability compared to the diamond wing shape of the F-22 or Su-57. Russia in the late 1990s could barely afford to feed its soldiers, let alone field a fleet of exotic, maintenance-heavy fighters made of expensive composites. The Su-47 was a luxury the Navy and Air Force could not afford. It was cheaper to upgrade the Su-27 fleet to Su-35's and develop a more balanced fifth-generation platform, the Su-57, than to industrialize the risky Su-47. The American X-29 was a smaller, single-engine demonstrator. The Su-47 was a full-sized, heavy fighter. While both proved forward-swept wings worked, the Su-47 pushed the concept much closer to operational reality. The fact that both nations abandoned the concept independently suggests the cons, weight, complexity, and stealth issues truly outweigh the pros, agility in the modern missile age. The Su-47 did not die in vain. It was the mother of the Su-57 Felon. The technologies matured on the Berkut form the backbone of Russia's current aerospace capability. The manufacturing techniques for large composite panels pioneered by Technologia for the Su-47 are directly used on the Su-57. The internal bay mechanisms and ejection testing validated on the Berkut enabled the internal carriage capability of the Felon. The flight control laws for unstable airframes were refined on the Su-47, allowing for the extreme supermaneuverability of modern Sukhoi fighters. Most importantly, the project kept the Sukhoi design team together and employed during the darkest days of the Russian aerospace industry. The Sukhoi Su-47 Berkut was a magnificent dead end. It was a machine that conquered the aerodynamic demon of divergence, only to fall victim to the prosaic demons of cost, fatigue, and changing tactical doctrine. It was too powerful in the sense that its aerodynamic capability outstripped the material and economic capacity of its era to support it sustainably. It remains a testament to the audacity of Soviet and Russian engineering, a fighter that looked like it flew out of a comic book, but whose DNA is quietly woven into the formidable Su-57s flying today. The Golden Eagle may never have entered the hunt, but it taught the rest of the flock how to fly.